Good evening. In this lecture, we will discuss Eulerian and the Hamiltonian graphs. Okay. So already we discussed a walk. Okay, a walk is what? A sequence of vertices and edges. So in a walk, vertices and the edges are repeated. Okay, so trial. So first, a walk with non-repetition of edges is called a trial. So that means only in trial edges is not repeated, but vertex is what repeated in a trial. Path, a trial in which vertices are distinct. So in a path, both vertices and the edges are what distinct. So cycle is a closed path. So these four definitions is already we discussed in that lecture. I don't know the lecture number. Next, Eulerian trial or Eulerian circuit or Eulerian tool. So, okay, so they will use different terminologies. So here it is given Eulerian trial. So what is Eulerian trial? A closed trial which traverses, or you can say passing through. Okay, passing through all the along traverses or passing along all the edges. Okay, exactly once. Okay, is called a Eulerian trial. But here the edges should cover all the edges exactly once. But here edges should not be repeated because it is a trial. Trial means what? Non-repetition of edges, but the vertex may be repeated. Okay. A graph G is Eulerian graph if G contains an Eulerian trial. So a graph, you can say a graph is Eulerian graph only if contains what? Eulerian trial. Okay. Next. Uh, so a path of a graph, okay, G is called the Eulerian path if it includes each edge of G exactly once. Okay. So Eulerian circuit is a little bit important than Eulerian path. Okay, but anyway, the definition is given in the book. A path of a graph G is called Eulerian path if it includes each edge of G exactly once. Okay, a circuit or a cycle of G is called Eulerian circuit if it includes each edge of G exactly once. Okay, but here it is path, here it is what? Circuit or cycle. A graph containing Eulerian circuit or Eulerian tour or Eulerian trial is called an Eulerian graph. Okay. For example, let us consider the graphs given in 3.51 and 3.52. Okay. So the graph G1 contains Eulerian path between what? B and D. So namely, path means the starting and the ending vertex are different, but it covers what? All the edges B, D, and then C. Okay, or B, D, C, and then again what? B. Vertex may be repeated. Edges should not be repeated. Okay, B, and then A and D. So you can check it. It covers all the edges exactly once. Since it includes what? Each of the edges exactly once. So from this is the Eulerian path from where? B to D. Or you can start from D, you can end with what? B also. So next, the graph G2 contains Eulerian circuit, namely A, E, C, D, E, and then what? B, E. Here starting and ending is what? Same vertex. So it covers all the edges exactly once, but the vertex may be repeated. since it includes each of the edges exactly once. So here G2 is what? Eulerian graph. Why it is Euler graph? Because it contains what? Eulerian circuit. But G1 is not an Eulerian graph because G1 does not contain what? Eulerian circuit. But it contains only what? Eulerian path. So the necessary and sufficient condition for the existence of Euler circuits and Euler paths are given in the following two theorems. So without proof is not needed. A connected graph contains an Eulerian circuit if and only if each of its vertices of even degree. Okay, so look at the previous example. Here the degree is what? 2, because this graph is, we told it's Eulerian graph. This is a degree 2, degree 2, degree 4, degree 2, degree 2. So all the vertices are what in this graph? Even degree. So that's why they are telling here. A connected graph contains an Eulerian circuit if and only if what? Each of its vertices is of even degree. Okay. Next, a connected graph contains an Eulerian path if and only if it has exactly two vertices of odd degree. Okay, look at this one. Here, this is degree 2, degree 2, degree 3, degree 3. So this graph contains exactly two vertices of odd degree. Okay, so two vertices of odd degree. So this contains what? Eulerian path. Okay, so the Euler path will have the odd degree vertices as its endpoints. Okay, okay. This is some important note. Okay, the in the graph G1, B and D are what? Degree 3 each. Hence, we have a Eulerian path existed between what? B and D. Okay, so because B and D are odd degree vertices, so we have a Eulerian path from where? B to D. So both odd degree vertices are endpoints of the path. Okay. In G2, okay, already we discussed all the vertices of even degree, are hence an Euler circuit is existed. Okay. Next concept. Okay, actually this is an Eulerian graph. Okay, this is not Eulerian because why this is Eulerian means maybe I need to draw this graph. Okay. Uh, Maybe this is useful. Okay, that's why I'll draw this one. So maybe I'll start from here. Okay, put vertices 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay, I'll start from here. I'll end with, I'll join like this. Okay, I'll go like this and then again. Okay, I'm going exactly once, but the vertex may be repeated. So I'll start from here and now end with here, but still it's not finished. And then I'll go like this. I'll go like this. Okay. Finally, I'll end with here. So this is the starting and the end point. Or you can choose some other vertex also starting and end points. So that's why this graph is what? This graph contains Eulerian circuit. That's why this graph is Eulerian graph. Okay, and also you can check the degree of each vertex. This is 2, this is what? 4, this is 4, this is 2. All the vertices of degree of all the vertices are what? Even degree. But here, this is even, this is even, this is odd, this is odd. So suppose if all the vertices of the graph is not even, then the graph is not Eulerian graph. Okay, that's all. Over. Because but this contains Eulerian path, because two vertices are what? Odd degree. So there is a Eulerian path existed between what? A and C. So I think maybe I think at least in the previous one. Okay, okay, where here also I showed there is a Eulerian path between what? B and D. So here, similarly, same thing you can. B there I joined what? B and D. Instead of B and D, here it is joined what? A and C. So that is a difference. Try to get a Eulerian path from what? A to C. Okay. Next, Hamiltonian graph. So Hamiltonian graph is slightly different from Eulerian graph. A cycle is a Hamiltonian cycle if all the vertices is present in the cycle. All the vertices is present. That means all the vertices are present exactly once in the cycle. Here, uh, uh, so if all the vertices are present exactly once means uh, the edges also exactly present one. But here there is no need to cover all the edges. Okay, so we need to uh, cover all the vertices exactly once. So here look at this graph. Okay, this is a Hamiltonian graph. Why? Because if we go like this, if we go like this, we go like this, it covers what? All the vertices, A to B, B to C, C to D, D to A. So it's a cycle. All the vertices are present in the cycle. That's why this is what? Hamiltonian graph. This is not a Hamiltonian graph. Even if I suppose if I start from here, E to D, and then A, B, C, D, and then again I need to come to D to go to what? E. So I told that all the vertices should be exactly once. Okay, and also we should find a cycle. So here you cannot find a cycle. That means what? Starting and end points are same, and you should go to all the vertices is not possible. Even if you start from A to B, B to C, C to D, D to E. Again, if I want to come to A, I need to come to again D. So that is not allowed in from the definition. So that's why this is not Hamiltonian cycle. Okay. So next, a path. Similarly, in Eulerian graph, we discussed Eulerian path and Eulerian circuit. Here also, Hamiltonian path and Hamiltonian cycles or circuits we are going to discuss. A path of a graph G is called a Hamiltonian path if it includes each vertex of G exactly once. Okay. Okay. Next, a cycle or a circuit of G is called Eulerian circuit if it includes each vertex of G exactly once, except what? The starting and the end vertex. Because starting and the end vertex are same, that's why that appears what? Twice. But here, Hamiltonian path means path means the starting and the ending vertex are different. Okay, that's why they don't tell uh, about the starting and the end vertices here. So it includes each vertex of G exactly once. Okay. Next, a graph containing a Hamiltonian circuit is called a Hamiltonian graph. That's all. So only thing, if you want to say a graph is Hamiltonian graph, it should contain what? Hamiltonian circuit or Hamiltonian cycle. Okay. So here, like in Eulerian circuit, so what is the necessary and sufficient condition for the Eulerian? So here it is we studied the necessary and sufficient condition for the existence of Eulerian circuit or Eulerian path is what? So Eulerian, the graph, a control graph contains the Eulerian circuit if and only for each of its degree is what? Each of its vertices are even degree. But here, uh, uh, in Hamiltonian, the necessary and sufficient condition for the existence of Hamiltonian circuit in a graph is not known yet still. So although a few sufficient conditions have been found, but that is not those sufficient conditions not included in our syllabus. Okay. For example, let us consider the graphs given in this figure and this figure. Okay. The graphs G1 has Hamiltonian circuit, namely A, B, C, D, A. Okay, it contains a circuit. Hamilton. Okay, so starting and end points are same. It covers what? All the vertices exactly once. So G1 has Hamiltonian circuit means G1 is what? Hamiltonian graph. Okay. But there is no need to cover what? All the edges. Okay. So that is already I told to you in Hamiltonian graph in Hamiltonian circuit we need to cover what? All the vertices. Okay. So G2, what is G2 is a Hamiltonian path. Why it is a Hamiltonian path? A to B, B to what? C, C to D. So it covers all the vertices, but the starting and the end points are what? Different. So that's why it is not a Hamiltonian. A to D is what? Is not a Hamiltonian circuit, but A to D, A to B, B to C, C to D is what? Hamiltonian path. So that's why this graph contains only what? Hamiltonian path. So and hence this is not a Hamiltonian graph. So when we say the graph is Hamiltonian graph, it should contain what? Hamiltonian circuit. Okay. So a few properties. Uh, from the graphs shown in the figure, the previous two figure, it is clear that the path obtained by deleting one edge from the Hamiltonian circuit. Suppose if I delete this edge from the Hamiltonian circuit, we will get a Hamiltonian path like this. So that is property number one. Okay. Also, a Hamiltonian circuit contains. Okay. So what is the meaning of two means? A graph containing Hamiltonian circuit, okay, contains a Hamiltonian path, but a graph containing Hamiltonian path need not have Hamiltonian circuit. So that is note 2. So note 3, complete graph Kn. So n greater than or equal to 3 is always contains a always Hamiltonian circuit, and hence the complete graph Kn n greater than or equal to 3 is what? Hamiltonian graph. Okay. So a given graph may contain more than one Hamiltonian circuit. Okay. These are some of the properties you should know about what? Hamiltonian cycles. Okay. Next. So find an Eulerian path or an Eulerian circuit if it exists in each of the three graphs. If it not exist, explain why. Okay, so look at this one. Okay, for Eulerian circuit, okay, Eulerian path or Eulerian circuit. Okay, so Eulerian circuit means all the degrees should be what? Even. So here, this is 2, degree 2, this is 2, this is 2, this is 3, 3. So already we studied a property. Suppose a graph containing two vertices of odd degree, okay, so it contains what? Eulerian path. Surely this will not contain Eulerian circuit. When a graph contains Eulerian circuit, it contains all the vertices of even degree. So this will not contain a Eulerian circuit. But the two vertices of degree, this is what? Degree is what? 1, 2, 3, 1, 2, 3. This is actually what? 1, 2, 3, 4. Yes, but this is 3. Okay. First you should write the degree here. 3, this is 3, this is 2, this is 4, this is what? 2. So these three vertices C, D, E are what? Even degree. Okay, but A and B are what? Odd degree. So suppose if we have two vertices of odd degree, then we will get a Eulerian path between what? A and B. Okay. So what is the Eulerian path? The actual Eulerian path is what? In G1 there are only two vertices, namely A and B are what? Degree 3, and all other vertices are even degree. Hence, there exists a Eulerian path between what? A and B. The actual path is A to B. B to E should cover all the edges. E and then D and then A and then what? A and then C and then D and then B. Okay, that's all. So A to B, I get a path. So this path is Eulerian path, as it includes each of the 7 edges exactly once. Okay. So in the graph G2, okay, how many vertices? 1, 2, 3, 4, 5, 6, 7 vertices. 7 vertices. Okay. But I think this is not a vertices. I think so because it is in bold. Okay. That is on bold because here in G2, 6 vertices of odd degree they are telling. Okay. That means I don't know why they put here Q. Okay, the reason why I'm not telling this is not a vertex means everything the other vertices are in bold, but it is not in bold. That's why I don't feel that here there is a vertex. Okay, 1, 2, 3, 4, 5, 6. 6. There are 6 vertices are what? Odd degree. Okay, 3, 3, 3, 3, 3, 3. Okay, so this should not contain what? Eulerian circuit because uh, the Eulerian circuit means the graph should contain what? All the vertices of even degree. So that's why this does not contain Eulerian circuit. When it will contain Eulerian path, if the graph exactly 2 vertices of odd degree, then only it contains what? Or Eulerian path. So and hence this graph does not contain both Eulerian circuit and what? Eulerian path. Here we'll check. Yes, we'll check the reason here. In G2 there are 6 vertices of odd degree. Hence G2 contains what? Neither an Eulerian path nor an Eulerian circuit. That's all. So G3. G3 is actually what is the degree? A degree 4, 4, 4, 4, 4. All of them are even degree. So and hence it contains what? Eulerian, Eulerian circuit, and hence this is what? Eulerian graph. So in G3 all the vertices are even degree. Hence there exists an Eulerian circuit in G3. So namely it is what? Okay, A to B, B to C, D, E, okay, E and then A to what? C, C to E, B, D, A. So it contains all the edges exactly once. So this is the circuit is Eulerian since it includes each of the 10 edges exactly once. Next problem. Find a Hamiltonian path or a Hamiltonian circuit if it exists in each of the 3 graphs as shown in this figure. If it does not exist, explain why. Okay, so first graph. So in G1 contains Hamiltonian circuit. Okay, check it. So A to B, B to C, C to D, D to E, E to F, F to A. So this is the path. This is a circuit. Sorry, Hamiltonian circuit. It contains all the vertices exactly once. All the vertices exactly once. Starting and the ending are what? Same point. So in fact, there are 5 more Hamiltonian circuits in G1. So please, you can find out. So okay. So and hence the first graph is what? Hamiltonian graph because it contains what? Hamiltonian circuit. So G2 contains okay, neither a Hamiltonian path nor a Hamiltonian circuit. Since suppose if I start from here A, B, C, E, F. Okay, if you want to come to D again, I should cross E. Okay, so suppose if I come like this A to B, B to D, E, F. Again, if I want to come to C, again I need to cross what? E. So that is here they are telling. Since any path containing all the vertices must contain one of the edges, either AB or EF, more than once. So that is not allowed in the definition of Hamiltonian circuit or even the definition of Hamiltonian path. So that's why this graph does not contain what? Hamiltonian path. Similarly, this graph does not contain Hamiltonian circuit. Okay, the next one. This is A, this is B. This is not D. Okay, wow. This should be what? B. This is C, D, E. So G3 contains two Hamiltonian paths from C to E. C to E, similarly what? From D to E. So C to, this is actually what? B. C to B, B to D, D to A to E. Similarly, I'll start from D, D to B, B to C, C to A to E. So both of them are what? Hamiltonian path. But we don't have a Hamiltonian circuit exist in G3. Next problem. Give an example of a graph which contains Eulerian circuit that is also Hamiltonian circuit. Okay, Eulerian circuit that is also Hamiltonian circuit. Okay, so the first this is an example. Okay, so this is an Eulerian circuit A, B, C, D. So because it contains all the edges exactly once. This is also a Hamiltonian circuit because it contains what? All the vertices exactly once. Look at the explanation. So the circuit A, B, C, D, A in G1 consists of all the edges and all the vertices each exactly once. Therefore, G1 contains what? Circuit, that is what? Both. G1 contains both Eulerian circuit and also what? Hamiltonian circuit. Next, give an example of a graph which contains Eulerian circuit uh, and Hamiltonian circuit, both, but both of them are distinct. For second one, this is an example. So you can see Hamiltonian is A, B, C, D, A. So this is Hamiltonian. Okay. Eulerian means A to B, B to D. Okay. B to, sorry, A to A to B, B to D in this way, and then again what? D to B, and then B to C, C to D, D to A. So uh, both Hamiltonian circuit and Eulerian circuits are different, but both of them are exist. You can check it. So G2 contains, okay, G2 contains Eulerian circuit. What is Eulerian circuit? A, B, D. Okay, check it. A, B, D in this way D, and then again D to what? B. Again D to B, and then B to what? C. C to D. Okay, maybe if I write, okay, maybe I'll take a snapshot. Okay. Okay, look at this one. Okay, subdivision 2. Okay, so G2 contains Eulerian circuit. Okay, A, B. Okay, look at, you can see this one. A, B, B to D, D to what? B, B to C, again C, and then D, A. Okay, and the Hamiltonian circuit already I told you A, B, C, D, A. But the two circuits are different. Okay, now next, the previous was third one. What is third one? Give an example of a graph that contains what? Eulerian circuit, but not Hamiltonian circuit. So Eulerian circuit, but not Hamiltonian. This is an example. Okay, because this contains all the vertices are what? even degree, 2 to 2 to 4. So what is the Eulerian circuit in G3? A to B, okay, A to B, B to what? C, C to D, C to D, D to B, B to E, E to A. Okay, it is mentioned here. Okay, this is what Eulerian circuit. Uh, uh, but uh, but but here you cannot find what Hamiltonian, because if I start from here, A to B, B to C, C to D, if I come to E, I should passing through B. So it is mentioned as the vertex B is what repeated twice. Okay, so that's why this does not contain what Hamiltonian circuit. This contains only what Eulerian circuit. Okay, next the fourth one. Uh, Give an example of a graph which contains Hamiltonian circuit but not Eulerian circuit. Okay, Hamiltonian circuit is just to start from A, B, C, D, E, A. You can check it. Fourth one. Fourth one. So fourth one, this graph, G4 contains a Hamiltonian circuit. A, B, C, D, and then what? E, A. So this is actually Hamiltonian circuit. How? Okay, this is Hamiltonian circuit this graph contains, but this graph does not contain the Eulerian circuit because all the vertices are not even degree. This is 2, but vertices, what is the degree of this one? 3, 3, this is 4, this is even, this is even, this is even, because this is 4, this is 4, this is 2, but these two vertices are what? Degree 3 and degree 3. So and hence all the vertices are is not of even degree, and hence this graph is not that does not contains Eulerian circuit. Okay, next give an example of a graph which contains neither an Eulerian circuit nor a Hamiltonian circuit. Okay, so here this is the graph. Why it is not does not contain Eulerian circuit? The reason is here degree 2, degree 2, degree 2. This is what degree 3, degree 3. So all the vertices are not even, and hence this graph does not contain what? Eulerian circuit. Even this the graph does not contains Hamiltonian circuit. Okay, why this graph does not contain Hamiltonian circuit? The reason is, okay, here it is mentioned. Okay, I need only this graph. So in G5, the degree of B and D, the degree of B and D are each of equal to 3. Okay, hence there is no Eulerian circuit because it contains odd degree vertices. Also, no circuit passing through each of the vertices exactly once. So that's why it does not contains what Hamiltonian circuits. I'll start from A, B, C, D. If I go to E, from E to A, there is no. If I want to go to E to A, I should go through what B. So if you go through B means you should cross. B occurs what 2 types. So that's why we don't find a Hamiltonian circuit in this graph. So this is an example of a graph which does not contain both Eulerian circuit as well as what? Hamiltonian circuit. Okay. Okay. This is an example already we discussed this one. Okay. So this is an example of a Hamiltonian graph which is not Eulerian. So why it is Hamiltonian? So A to B, B to C, C to E, E to D, D to D to A to B, B to C, E to E, E to D, D to A. So it goes through all the vertices exactly once. So and hence it is Hamiltonian, but it is not Eulerian. The reason is the degree of C is 4. So even remaining A is what? Degree 3. B is degree 3. So all the vertices are not even. So that's why this is sorry. Yeah, is correct. So for this contains this contains a Hamiltonian circuit, but this does not contain what? Eulerian circuit. The reason is all the vertices are not even degree. That's why this is what? Non-Eulerian, okay, or not Eulerian. Still, we have two more theorems. Okay, one another theorem. Maybe I'll check the time. 7:30. Okay, so okay, I'll stop here. The two theorems I will take a little bit later. Okay, thank you.